Alright, it's been a while since I recorded any videos for machine design, so let's try another one. Here I'm going to show why in combined stresses 3D Mohr circle has three principal stresses. And begin with a simple example where, let's say we have a tension in the y direction of 20 psi, 20 ksi. It doesn't really matter for our purposes. And on the x direction we have 80 ksi. All right, so look at each side, each face, or one of the three faces. The other three faces of the six are just going to be the same thing. Take a look at it, at each of these faces perpendicularly. So let's take a look at the XY face. That would be this face right here. We're going to take a look at the XY. We could see that it's going to have 20 in that direction and 80 in the X direction. So we'll draw it on the other side too, just to be very, very thorough. Now, where would these appear in the way that we draw a Mohr circle? Okay, for this right-hand face, it would end up being right here, right? Because there's no shear on it, so this point is going to be on the 0 of the shear axis, and it's going to be 80. And now this point on the top is going to be at 20. So we could draw a Mohr circle right here. That's the Mohr circle for this face. Now let's take a look at the YZ face. Okay, the YZ face is going to be this face right here. So we're looking at it. So the 80 is out of the plane. So we still have 20 right here. I'm squeezing it in. And 20 right here. But it's 0 on this face. So if we plot this point, that's going to be this point. But then for this little square, it's going to have this other point it's going to have 0 as a principal stress. So here is the other Mohr circle for this piece. Okay, now let's take a look at the last face, the XZ face, which is going to be this guy right here. So in the X direction, as we see, we have 80. And in the Z direction, we have 0. Okay, so let's plot out that point on here. We have 80 right here. Be better if I drew in another color. So let me get the other color. There's blue. I'm picking blue. All right. So we have this point, and then on the top face we have 0. So the Mohr circle for this face, for this right here, the XZ face, is going to have this point and this point. That's the idea of why you have 3 Mohr circle. And here's a second example, right, just to make it more clear. If you have compression on the Y face, or I should say on the XZ face, and you have compression on the X face, or maybe we could call it the YZ plane face, and you have on these other faces on the opposite side, and you have, say, 80 ksi here and 20 ksi here, right? And so it matches. We can start out by plotting the XY face again, and on the XY face we have 80 and 20, and we can plot that one, but this time it's going to be compression, so we're going to have 80 and 20. So we end up with a Mohr circle like this, right? And I'll change color to keep it clear here, and maybe go green. And now we could go for the YZ face, YZ right here, which is that YZ plane. It's going to be this face right here. We're going to have 20 going down, and compression 20 right here. Nothing on this Z direction. All right, so plot the point right there. It's going to be 20 in compression and 0. So there's a Mohr circle. And then finally, we can do this face the XZ plane, and we're going to have 80 in the X direction and nothing in the Z direction, both in compression. So it's 80 right here and nothing right here. So now we have this other Mohr circle. Why is this important? Because if you want to figure out what the maximum shear is in a cube that you've chosen on your piece and you're in the stress state, and you want to find out what the maximum shear is, you have to be careful not to just look at one plane. In that one plane, that would indicate that that right there was the maximum shear. But if you take a look at the 3D version, you find out that actually there is a greater shear that could be accomplished if you were to change and rotate in some type of fashion the cube so that it had a different type of reference. The reference that you pick, by the way, is arbitrary. So just because you line up something with an X, Y, and Z axis, that doesn't mean that the piece of steel, the little very micro small piece of material, is going to be lined up with that axis. So that's why you can transform, you can twist the axis and then discover that the actual piece is experiencing a larger shear than you had anticipated with the default XYZ. Now, and the same thing down here, where we're going to find that we're going to have the absolute maximum, sometimes the Lord ABS comma max, for this big shear, which is going to be greater than either of the maximum shears that you would find otherwise. And this is going to be important in one of the big failure theories, the maximum shear stress theory, also known as Tresca. That's going to be an important factor to consider. And that's all we have for today.